Welcome back. Today we'll finish up with data structures, in particular hashing, and then we'll use the rest of the time for a midterm review. Your midterm is tomorrow, and we'll go over the details of how that's going to work. You'll have a 24-hour window in which to complete it and hand it in. All right. So just to continue with, or just to rehash what we were doing on Friday, we were looking at hash-based data structures. Hash-based data structures use traditional old arrays, but they use this hash function to map an individual element to a particular location in that array. The way that works is if you've got just a general object, usually a language has something built into it, like say Java has hash code built into all objects. It's inherited from the object class. By default, that uses the Java virtual machine memory address. Of course, you can modify that so that you can come up with a hash function that is completely dependent on the state of the object. Once you've got that, then you've got an integer. Once you've got an integer, then you can push that through a hash function. The hash code method is not generally a hash function, but instead it gives you an integer representation of that object. Once you've got that integer representation, then you can put it through a hash function. A hash function is nothing more than something that maps a very large domain to a smaller codomain. And for our purposes, we were looking at integers, the set of all integers, right? Mapping to a subset of integers, z mod m, where z mod m is defined as 0, 1, 2, up through m minus 1. That's convenient because that's indexing. That tells you what the index of the object of the array, the object should be stored at. Okay. Immediately, though, when we went through our examples, we came up with a problem, right? That we could have a hash function. Ideally, a hash function is going to evenly distribute things. But unfortunately, because you are mapping let's undo that. A large domain onto a small codomain, that necessarily means that you will have what are called collisions. That there could be an x1 and an x2 that map to the same value here. That is, the hash function value of h1 is equal to the hash value function of h of x1 is equal to the hash value function of x2. That means that the function basically is not one-to-one, right? Remember one-to-oneness? If you've got a domain and a codomain over here, right? When you've got x1 and x2, two distinct elements over here in the domain, and they map to the same element over here in the codomain, then this means that it's not one-to-one. Or an injection or surjection, whichever it is, who cares? A one-to-one is the terminology that I use here. That's certainly possible. In fact, it's expected because of the nature of a hash function. The nature of a hash function maps a large domain down into a smaller codomain, and so necessarily by the pigeonhole principle, you will have elements that collide, that end up going to the same position. So how do you deal with that? We briefly looked at a couple of collision resolutions, right? Collision resolutions, right? So one thing that you can do is called open addressing, and that's what we looked at on Friday, right? So if a collision occurs, you can simply map it to a second value in another location, right? Index. And when I say location, I mean index, okay? There are lots of strategies that you can use. The strategy that we used on Friday is called linear probing. Right? Simply go to the next adjacent cell, right, index, and if it is empty, use it. Right? That is, keep going until you find a free cell in order to store it. Right? You can also use quadratic probing. Use a quadratic function to probe for another open location index. All right. So instead of just going to the next and the next and the next, you can also use a different type of linear function where you can jump ahead 5 cells, or jump ahead C cells where C is some constant. Or you could use a quadratic function. And this one means that you are jumping by very large amounts, and then you always, of course, you wrap around. Whatever strategy you're using, you generally have to wrap it around. You generally wrap around to the start of the array when you reach the end, right? And the way that that's accomplished is, of course, through that mod m factor that we put into our hash function. You'd use that as well in your open addressing scheme. Or you could use double hashing, right? You could also use a secondary hash function to rehash it. And each one of these contains advantages and disadvantages. Some of them are more efficient. Some of them are less efficient. Some of them have better properties of reducing the number of collisions or secondary collisions, right? Because even if you do probe, right, as we saw with the example last time, then there might not be an available cell at all, right? And in which case, the hash table is full. Now you have to take care of that situation, right? So other considerations, right? So if the hash table is full, you need to deal with that somehow, right? And we'll talk about that here in a moment. Eventually, or if you want to support deletion of elements, you will need to keep track of which cells have been used before, right? Because again, when you search for this stuff, you use the exact same criteria that you use to put stuff into the hash table. So if you're using linear probing, right, and it mapped to this location right here, but unfortunately that was full, so we'll go ahead and put it over here. We'll go ahead and put it over here. Nope, those two are full. And finally, oh, this is the next available free cell. That's where we end up putting it. If we ended up deleting that thing that was already there, we need to keep track of that, because to resolve, okay, well, that's not the thing that we're searching for. Is that thing that we're searching for actually in the table or not? Then we'll have to take the same strategy of linearly probing it or quadratically probing it, or using another whatever strategy until we find a location where the item is, or we come to an empty cell that has never been used before. I like to call these dirty bits. This is you're just setting a dirty bit that this cell has been used before. It comes from memory caching. I don't know if there's a better term for it, but it's often used in memory caching. That you set this dirty bit to indicate that it's been updated. Or it hasn't been updated, depending on what you're trying to do in the cache, and that tells the operating system or the hardware or something that this memory cell has been affected or unaffected. So do with it what you will, right? You just need to keep track of that kind of stuff. And also, of course, as the table gets fuller and fuller, collisions are much more likely. In fact, if you get to a point where you've filled up the hash table and you can fill it no more, and so you go back and, okay, well, you end up deleting everything as well. Now all of the dirty bits are set to 1, right? They've all been used at some point, even though it's empty. And now everything basically devolves into linear search, right? All operations become inefficient, right? Order n for searching, insertion, and even deletion, because you, of course, to delete something you have to search for it. So even if it's empty, even if it's all empty, but this one element that you're looking for, right? And you hash it. You start out over here, and you have no idea whether or not that element is in there. You end up having to do linear probing all the way to get to that element, meaning that it's no better than if you just use a regular old array and then relied on linear search to do all of your functionality for you, right? So it can devolve after some time into just a regular old array. An alternative that's not going to solve this problem, we're going to solve that problem here momentarily, but an alternative is to use what's called chaining. Right? So instead of probing for a different cell, you store multiple elements at the same location / index. Right? To store multiple elements, you need another data structure. Right? So for that, let me go ahead and go back over here to the tablet, and let's look at an example. In fact, I'm going to pull an example from one of the midterms that we're about to do a review on. So I think it's down at the bottom here. Yeah, let's do this. So what we want to do is we want to, you can't see it, of course, but I'll say that I'll repeat it over here. What we want to do is we want to insert elements 9, 5, 1, 3, 2, 7, 6, 4, and 8 into an initially empty hash table. Let me move it down there so that I have room up here. Using the following hash function. H sub k is equal to 3k plus 5 mod 13. So in other words, our hash table here is going to be of size 13. I won't draw them all until we have need to, but 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, all the way up to 12, right? Etc. So let's review how this works with linear probing. We'll get to collision resolution here in a second. But otherwise, h sub 9 is equal to 3 times 9. So that's 27 plus 5. That's going to be 32 mod 13. And at this point, I'm going to go ahead and, I'm going to use Wolfram Alpha here. So 3 times 9 plus 5 mod 13. There we go. We'll use this over and over here. This is going to be 6. 3, 4, 5, 6. So 9 gets stored at 6. There we go. H sub 5 is going to be 15, that's 20, so I can do that one in my head. That's going to be 7. So right next door, 5 is going to be stored. H sub 1, that's also going to be easy. That's 1 times 3 plus 5, so 8. Mod 13, the remainder happens to be 8. There we go. H sub 3 is going to be 3 times 3, 9, plus 15, that's going to be 14. Mod 13 is going to be 1. So 3 gets mapped over here. 2. 2 times 3, 6, plus 5, 11. And so 2 gets stored over here. I gave myself way more room than I needed to, but okay. 9 and 10. There we go. All right. H sub 7. That's going to be 21 plus 5. That's 26 with a remainder of 0 because it is evenly divisible by 13. So 7. H sub 6 is going to be, hopefully there will be a collision here eventually. 8, otherwise it's good review at least. That's going to be 18 plus 5, so that's 23. That's a remainder of 10. 6, 4, and 8. 4 is going to be 12, 17, so 4. 4 gets mapped to itself. It's a fixed point, kind of. 8 is going to be 24, 29, so 1. Finally, at the end here, we have a collision, or only one, all right? At least for this example. Normally what would happen with linear probing is that we come over here and we want to insert 8. Unfortunately it's full, right? We don't have room here to insert it at index 1. So linear probing would go over 1, right? And that's available, so we would end up inserting it there. Quadratic probing would jump over by some quadratic function over here, right? But chaining means that these are actually not stored directly in the array. Instead, the array is referring to, let me go ahead and get rid of this. Instead, the array is referring to another data structure. It's a reference to, say, a linked list. 3 was there before. And you can always add to the end of a linked list or to the beginning of a linked list. It doesn't really matter. And those are all efficient operations. So I'll just go ahead and add 8 to the end of this. And likewise, you can redraw the entire the rest of this. And instead of storing the value immediately, you store it in a linked list. Alternatively, instead of a linked list, this could be a balanced binary search tree. Right? Or it could even be another hash table. But if it's another hash table, why do you have 13 hash tables here when you could just make one hash table that's even larger? A hint as to how we're going to resolve this stuff. You have no problem here with not finding space. You can make an arbitrarily long linked list all the way down the line. You can always add something more, as long as you still have memory in order to do it. Right? But there's a problem here, right? What's going to happen eventually is that if I have a hash table of size 13 and I insert 1,000,000 elements, I don't really have a hash table anymore. I just have 13 distinct linked lists. All of the operations take maybe 1/13 as much time as it did before, but it's still going to be a linear operation, right? So even with chaining, then it still devolves, right? Each cell is a reference to another data structure, such as a linked list or a balanced binary search tree or something else entirely, right? Instead of probing, the element is simply added to the data structure, the secondary data structure, right? But again, as I mentioned, the problem is still that then it starts to devolve, right? If you insert a lot of elements, then it really isn't any better than the secondary data structure you're using, right? And what I mean by that is example of searching becomes order n, right? It might be 1/13 of n originally, but it's still going to be order n, right? And so it really doesn't buy you anything in the long run if you do this without what's called rehashing, right? So rehashing. Regardless of which strategy you take, eventually you are going to hit your limit. Here, just let me check here for a second. Remember that we are on Piazza and YouTube. If you have any questions, post to either one of those, and I will see you. Otherwise, at some point, the performance will degrade, right? With more and more elements, all these cells become full or dirty, or the secondary data structure becomes large, right? And with if it's a linked list, then of course again it becomes order n. If it's a binary search tree, then you're a little bit better. That's going to be order log n, but still it's not. It kind of kills the intended constant time performance of your hash function. Okay. To resolve this, you periodically rehash and rebuild the table, right? That is, you create a larger array, right? And then with a different hash function, because again, your old hash function was mapping 0 through m-1. If you make a larger array of size m2, then you need to use a hash function that utilizes m2. Otherwise, you're only using a small part of the array, right? To remap / rehash all of the elements, right? And of course, if you're setting a dirty bit or something like that, then all of that gets cleared out, right? Rehashing, unfortunately, is generally order n. Because if there are n elements in the table already, and you create a new array that's larger, you still have to put all of those elements into the new array, which means that you have to go through all of those elements and recompute their hash function, put them all over here, and if you have a collision, you'd have to resolve those collisions as well. But the idea is if you were like 1 million elements to begin with, and you've created an array of 2 million, well, now you've got room to grow, right? And your performance goes back to being constant time, right? So over the lifetime of the data structure, the average performance is quite good, right? For most operations, it will be order 1, right? So it's all efficient operations. Occasionally, you will need to rehash, giving order n. But hopefully, that's not that often, right? Hopefully, that's every millionth operation or something like that. I'm just pulling numbers out of the air here. Hopefully, rehashing is only like 1% of your operations. If 90% of your operations are constant time, and only 1% of your operations there's a spike in complexity, then if you take a look at the average, if you average that all out, then it can be quite good, and we call that amortized constant time. Right? I don't have a very good actual graph of this, but here's what it might look like, right? Something like this. Right, we're mapping performance here now. Okay, so here's an x and y axis, the best that I can draw here, and down here, this is going to be time going forward. The data structure is created here, and then operations are performed throughout time, and maybe that it dies over here. You're done using it, and here we'll have performance. Or time, basically, right? That it takes a lot of time. So as with time, as you do more and more things with this hash-based data structure, and it starts to get full, then the time it takes to perform any one operation might grow, and then at some point it's no longer tolerable. So you say, okay, well, it's too full. The performance is degraded too much. So let's go ahead and rehash everything. Then there's this spike in performance because, of course, you have to rehash all these elements. But after that, it drops down, right? And you've got your performance back to being constant, basically. Constant. But as it gets more and more full, then the performance starts to degrade. At which point, again, you rehash everything, causing a spike in performance because you have to, all those millions of elements that are in there or whatever it is, have to be rehashed. But then it goes back down, right? And maybe it's a little bit better for a longer period of time, but eventually it goes back up, etc. And so you have these spikes and these troughs. But when you take the average, right, these spikes here are not that common. It's only every, say, million operations or something. If you don't focus on the worst case scenario here, like we do usually with big O analysis, instead, from a practical point of view, look at the entire performance with respect to the lifetime of the data structure. When you average these out, right, then it looks more like, it's going to be higher than the best performance, but it's certainly going to be lower than the worst performance. And when you average them out over the lifetime, then it looks kind of, constant, right? This is why we call it amortized. That's a term borrowed from finance and business, where you want to look at the cost of a loan. You amortize that cost over 30 years or something like that. And then you can bring inflation into it. And, we like long loans because 30 years from now, the money will be worth less. And therefore, it's like your loan has basically disappeared due to inflation, or it's gone down a little bit due to inflation. So you have to look at the amortized analysis, the amortized cost of a loan, or in this case, the performance of a data structure over the long term. When you look at the long term instead of just short term, right? Short term, oh, that's terrible, that's terrible, that's terrible. Short term, oh, that's great, that's great, that's great, right? But when you look at it over the life of the data structure, then it's not as great as these troughs down here, but it's certainly not as bad as these spikes in performance up here. So from an amortized point of view, it is actually a pretty good data structure, and that's why it's the go-to, right? The very first thing that you should use is, I'll use a hash map, or I'll use a hash table, or something like that. And for like 90% of your applications out there, again, I'm just pulling that number out of the air, but for 90% of the applications that you might have, probably want a hash-based data structure. Like a hash table, like a map, or something like that. All right. So, how do you know when to rehash? Right. You generally keep track of what's called a load factor, right, to decide when to rehash the table. Right. That's n divided by m, where again, n is the number of elements in the array, or in the hash table, right? Oops. M is the size of the hash table. Remember, we were using that mod m so that we could map from 0 to m minus 1. And as an example here, suppose that n divided by m is equal to 0.75, right? What's the interpretation here? It means that the table is 75% full, right? And so you can actually tune this. In fact, in library implementations, you can usually provide this at instantiation. For example, in Java, if you use hash-based data structures, you can provide a load factor when you create it as an option. I don't know what the defaults are, but you can play with that. I don't want to I'm risk averse. I don't want to have this degradation of performance. So let's go ahead and set that low. When it's 25% full, then rehash everything. Right? I want to make sure that that's going to be expensive, but I want to make sure that my hash table is not very full at any time. If it goes below a certain threshold, then of course you can rehash to a smaller table if you want to. Or you could go the other way and say, well, I know I'm going to put stuff in, but I'm not going to take a lot of stuff out. And once it's in there, I'm not going to put anything in there because I'm loading from a file, say. I'm loading 1 million elements from a file, and then I'm going to work on those and work on that data. But I'm not going to be taking things in and putting them out, right? So maybe I'm a little bit more hesitant for rehashing. I could just say 0.95 when it's 95% full. Then go ahead and rehash. There are things called perfect hash functions, where if you know up front how many things you're going to be putting in and you're not going to be putting in any more, you can actually construct a hash function that is perfect in that it has no collisions whatsoever. Right? So that's another area of research if you're interested. But basically, this load factor gives you what's called a trade-off. Generally, this means that a hash table is a time-space trade-off data structure. And what I mean by that is that you can have a smaller table, right? But that means that there are more collisions, 1s in collisions. That means that there's slower access or insert, etc. But there's also less wasted space. If I went to one of those extremes and said, I only want my hash table to be 10% full, and then once it hits that threshold, create a brand new hash table that's even bigger. Well, that means that you're wasting 90% of the space at all times. And you might not be able to do that, especially on a small system with small memory, right? So you might go the other way. Larger tables, of course, then would have fewer collisions and faster operations, but more wasted space, right? So it's a time-space trade-off here. And finding that balance, that's where the load factor comes in. You can say that, well, I've got a lot of memory, but I don't have a very good processor. So I want to optimize for that, and I'm okay with more wasted space because I've got space to spare, right? Or you could go the other way. I've got very limited space, or I have a lot of space, but the cache hits and misses. Those are what's killing my performance. Then you can go with a smaller table and end up with more collisions and slower overall operations, but then there's less wasted space, right? So that is, in a nutshell, all I wanted to cover with respect to hashing. It's really the ultimate data structure. It's not the ultimate. If it were the perfect data structure for all situations and all applications, we wouldn't even talk about trees, binary search trees, graphs, whatever. We would just use hashing everywhere. But there are situations in which you want different performance, and you want different aspects because your performance lies elsewhere, right? But otherwise, again, in practice, for all practical purposes, 90% of the situations you're probably going to want a hash-based data structure, whether or not that's a map or a hash table or something like that. Okay. I see no questions yet, but that brings us to the end of what's going to be covered on the midterm. So how is the midterm going to work? I'll go ahead and write the notes here. Right? The midterm PDF handout will be automatically posted to Canvas at midnight tonight. Right? So midnight, morning of Tuesday. You will have 24 hours in which to complete it and hand it in to Canvas. They're all written. There's no programming on it. They're about 5 questions. I've not yet finalized it, but I have written it. And I'll be cutting it down to 5 questions here later on and putting it up to Canvas. It'll auto open, it'll auto close 24 hours later. You can, if you need to, you can turn it in partially and then come back and you screwed something up. I do believe that you can hand it in multiple times. You are to work alone. You are to work individually. No partners, no collaboration at any level. You feel free to ask questions on Piazza. Others should refrain from answering. We'll go ahead and take care of those. But you can ask questions. We'll give you as much clarification as necessary, but we won't be helping you to the extent that we help you on the assignments, of course. It's 10% of your grade. It's 100 points, 5 questions, 10% of your grade, right? And that's pretty straightforward. I don't see if you have questions about what it's going to look like, let me know. But otherwise, I'll show you here what past midterms have looked like. All right. In fact, let's go ahead and go to that now. Here's the midterm from last summer, and we'll go back and forth, and we'll do this as much as you want, as much as we have time for, at least. The last thing I wanted to mention is that there will be no live stream on Tuesday. Instead, extended Zoom office hours. All right? So I won't be broadcasting, but I will still be available from 11 to 12:30 as well, in addition to my regular office hours. So if you have any questions, you can stop by during the regular live stream time. All right? That's the only other thing that I wanted to add there. Otherwise, here is here's the midterm from last summer, excuse me. Let G be an undirected graph. An independent set of size k in G is a subset of vertices of size k, such that no two vertices are connected by an edge. They are independent. That is, for all x and y in that independent set, they are not connected by an edge. Design an algorithm that, given a graph G and a positive integer k, determines if G contains an independent set of size k or not, provides sufficient pseudocode, and a full analysis of your algorithm. Right? For that, I'm just going to go ahead and go to the tablet here. So to understand this is why you have 24 hours, to fully read and understand each one of these things. Here's a graph. And you might remember in class, we covered what a clique is, or a clique, right? Here is a clique of size 3. It is a subset of vertices that are all connected, right? So I could add additional edges here, and now this is a clique of size 4. An independent set is just the opposite of that. An independent set is a set of vertices that are not connected. So, for example, I could take this vertex, and then I could also take this vertex, and that's an independent set of size 2, right? Because there is no edge between them. Right? So, is there a larger independent set here? Right? Well, I could take this vertex and this vertex. They're not connected by they're connected by a path, yes, but they're not connected by a direct edge going between them. All right? And then I could also select this one over here. There is an independent set of size k. None of these three vertices are connected by an edge. So the answer, if I were asking for this graph, is there an independent set of size 3? Then the answer is yes. Okay. Hopefully that's enough to understand. Now, the connection that I was trying to help make there is that it's just the opposite of a clique. So if we take the same algorithm that we did when we brute forced a clique, then we should be able to solve this problem with just changing the criteria for whether or not this thing is a clique. Right? So here's my input. Here's my good pseudocode. Right? A graph G equals V comma E and an integer K. And I believe we said that it had to be greater than, strictly greater than 1. Otherwise, if K is just 1, then any vertex by itself is independent because there's nothing else in the set. Right? And an integer K. Output, yes, if G has an independent set of size K. Right? Now, pseudocode, right? All you need to do is generate subsets. That's the very definition of an independent set. It's a subset of vertices. So for each subset I of vertices, you need to check to see if that is indeed an independent set. So for each pair of vertices, x and y, in that independent set, in fact, let me give myself some more room here. There we go. I'll make a flag variable here. Is independent set. Is I set there. And we'll assume that it's true, right? Until we find that it's not. Okay. So for each x and x pair of vertices in that independent set, potential independent set, if x and y are connected, they are an edge, then is I set will be set to false. We found a counterexample there. Right? Those two particular vertices are connected, so therefore this is not an independent set. Right? All right, so if is I set, then output yes. Otherwise, if we get through all subsets and none of them are an independent set, then we output no. Right? Now, there is a mistake that I made. What are we doing? Here, we're doing all possible subsets. Remember that we are looking for subsets of size k. Right? So what I want is all subsets I, and then let me go ahead and erase this part right here, such that the size of I is equal to k. Then we'll do all this. That's the magic of pseudocode, right? You can omit the details. If I were doing this with the combination, I could throw that combination algorithm that we developed in the first week on brute forcing, generating combinatorial objects, in which case I would set my k, and I would only generate objects or subsets of size k. If I were doing this using backtracking, I would go forward until I have made a set of size k, and then I would never add anything to it. I would then start backtracking. Of course, if I ever found an independent set, then I would immediately stop and output yes. But I wouldn't have to create a subset of size k plus 1 or a subset of size k plus 2. Or for that matter, I wouldn't have to do all these checks for any subset that is size less than k. Right? So hopefully it's pretty straightforward to analyze this. One, the input is the graph G. Not the integer k, because of course G will has more, potentially way more vertices than k. In fact, it should. The input size is going to be the size of the vertex set, which we always label as n. 3, the elementary operation here. I would say that it's simply just checking this entire thing. I would roll that up into one operation. Checking if it is an independent set. Right? Yes, there's another for loop here. And so if your elementary operation was checking if something is an edge, then yes, it's going to be way more complex than this. This would, of course, would be k choose 2, right? I'll put that in red over here. This would be order k choose 2, which is order k squared. But if k is going to k is not our input here, right? The n is our input. So that's why I'm safe here in rolling this all up into one operation here. Okay? Because we want the performance with respect to n, not k. K squared sitting out front, who cares, right? So 4, how many operations, how many times is that executed with respect to the input size? Well, how many subsets are there of size k? And choose k. And 5, provide an asymptotic characterization of that. Well, it's going to be order n to the k. So again, if k is a constant, then you are in polynomial land, right? And it's efficient. That is not true in general. If I have a graph with 1,000,000 vertices, and I want to know if there is an independent set of size 500,000, right? That is going to be the worst case scenario. That's going to actually be exponential, right? And so k, you can't consider k to be a constant in general here. K could be, but as far as this analysis is concerned, it's okay to leave it like this. Okay. Can you post an example midterm to Canvas? I probably won't because it's right here, right? You could go ahead and pause and take a screenshot if you want, right? Okay, here it is again. So, part 2, A maximum independent set is an optimization problem that, given a graph G, outputs the size of the maximal independent set in G. That is the independent set with maximum cardinality. So suppose that you have access to an algorithm that we just wrote basically above, that takes G and K and solves the independent set problem from the first question. So take everything we just wrote, package it up into a function that's in a library that we don't care about how it actually works, right? We just like square root, we can call it. A outputs true if G has an independent set of size K and false otherwise. A. Use the algorithm A to solve the maximum independent set problem and provide complete pseudocode. Okay? And then 2, suppose that A operates in order n squared time. That is certainly not the case. This is just suppose. Provide an asymptotic characterization of your algorithm. Okay? All right, so back over here. Again, we have access to this algorithm A that takes G and K and outputs yes if G has an independent set of size K, no otherwise. Right? Okay, so that's what we have access to. My input here is going to be a little bit different because we are just given the graph G. Right? And our output is going to be the size. What does it ask for? Solve the maximum independent set problem. So our output here is going to be the size. This is an optimization problem, not a functional problem. Remember, a functional problem would actually give you the maximal independent set. We're just asking for what is the size of the maximum independent set of the max independent set. All right. So hopefully this is straightforward. Just start with the largest subset that you can, right? Or actually, no, let me go ahead and go with K here. Started at n, right? And ask this algorithm, A sub G and K. If that says yes, then that means that you have an independent set of size n. That's as big as it can be because that's taking all the vertices. If no, try n minus 1, ... And that tells you that you should be running just a simple for loop. For K, running from n down to, now the trivial independent set is going to be a single vertex here. If A, G, K answers yes, says yes, then output K, the size of the maximum independent set. Otherwise, I mean, you don't have an otherwise here because eventually you will get down to 1, and unless it's an empty graph, the answer will be one of these things in here. It could be a trivial 1, right? And so I don't need an else down here or another case or anything like that. It eventually will say yes. Okay. So what is the analysis here? Well, 5-step process, of course, but the elementary operation is going to be a call to the algorithm A, right? Now part B, and so how many times does it do that? Well, it only does this for, this is 3, 4. It only does it at a maximum of n times. Right? In fact, you don't have to do that last iteration technically because you know trivially, as long as it's not an empty graph, that you have an independent set of size 1. So you could stop short at 2, and if that's not the case, then output 1 down here, saving you 1 call, but it really doesn't matter, right? Because it's still going to be order n, right? If you consider this to be an elementary operation. Now in part B, it changes it a little bit. Suppose that A is order n squared. Then what is the complexity of this algorithm right here? You can't consider that to be the elementary operation anymore. I mean, you can, but it doesn't cost you just 1 anymore. It costs you order n squared. And so the answer here would end up being n times n squared, which is going to be order n cubed. There There we go. Okay. Gomer question, is an enthusiastic but naive computer scientist. After seeing Karatsuba multiplication, Gomer has found another valid formula such that the divide and conquer approach will result in only 4 recursive computations on numbers that are half as many digits with no non-recursive multiplications required, just like Karatsuba. Assuming Gomer's algorithm is correct, is it better than Karatsuba? Okay. So first of all, let's understand A first, and then we'll go to B. So again, he has found a valid solution here where the number of multiplications, and so here's the strong hint that you should be setting up a recurrence here, 4 recursive computations on numbers that are half as many digits, and then no non-recursive cost. Okay. So if I applied the master theorem here, this would A would be 4, B would be 2, and D, of course, would be 0. And at this point, we bring in the master theorem. There we go. No memorization required. Just look it up. 4 versus B to the D. In this case, B is 2 to the D. And so we've got a strictly greater than here situation. And we've got that Gomer's solution here is going to be order n to the log base 2, that's B, of A. There we go. Which you don't even need to pull out your calculators for that. Log base 2 of 4 is going to be 2. So this is going to be order n squared. Is that better than Karatsuba multiplication? No. That's no better than grade school multiplication, long multiplication that we started out with when we presented Karatsuba multiplication. Right? Gomer tries to do the same thing with Strawson's matrix multiplication. He claims to have found an algorithm that requires only 3 recursive multiplications on matrices half as big, but requires 3n non-recursive multiplications. Is Gomer's algorithm likely to be correct? Why or why not? All right. So, again, the number of multiplications, set up your recurrence. It said 3 recursive multiplications on numbers that are 1/3 half as big. There we go. But it requires some non-recursive cost here, 3n. Again, applying the master theorem, 3, B is 2, and D in this case is going to end up being 1 because we do have a linear factor over here. So bring in master theorem once more. And what is our comparison here now? 3 versus 2 to the first. So 3 is greater than that. And we have, yet again, case 3 here. And so Gomer's purported solution is going to be n to the log base 2 of 3. There we go. Order. Now here you would have to pull out your calculators. I'll do it really quick for you. Log base 2 of 3. There we go. It's going to be about order n to the 1.5849 blah 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 blah. All right. Now the question originally was, is his solution likely to be correct? And the answer is probably no, because if you have a matrix with n squared elements, you have to at least look at all of them, right? Unless you're doing some heuristic or you're exploiting some additional structure of the matrix, you still need to look at all n squared of the entries, right? Remember that it's n by n. And that means that you need to at least look at n squared operations in order to get an accurate answer. Gomer here is claiming that you can do it without essentially looking at a good chunk of the input. It's unlikely that he has actually come up with a correct algorithm for those reasons. Okay. All right. Answer the following questions involving tree data structures. Let T be a regular non-balanced binary search tree with n nodes. What is the maximum possible balance factor for any node in T? Okay, so let's start considering some examples here. What about a tree with 3 nodes? How could we maximize its balance factor? By forcing it to become as skewed as possible. Left, right, it doesn't matter. As long as we've forced it to become extremely skewed. Remember, the balance factor is going to be the height of its left subtree minus the height of the right subtree. So the balance factor here for the leaf is 0. The balance factor for this one is going to be the height of the left subtree, which is 0, minus the height of the right subtree, which is -1. An empty tree, right, is always going to have a height of -1. So this is going to be +1. It's skewed to the left. Likewise, this is going to be 2. The height of its left subtree is 1. The height of its right subtree is -1. So 1 minus -1, 1 minus -1, there we go, is going to end up being 2. That's just for a 3-node tree. What if we were to have a 4-node tree here? And again, completely skew it to the left. Then it would necessarily have a balance factor of 3. Now let's generalize this, right? For a tree of 3 nodes, then the maximum balance factor was 2. For a tree with 4 nodes, the maximum balance factor was 3. And you can kind of imagine what the pattern here is going to be, that if we have n, then the maximum balance factor is going to be n minus 1. It's completely skewed one way or the other, or is skewed in a zigzaggy way. Okay. Let H be a heap. What is the minimum possible balance factor for any node in T? And then, without coming back here, what is the maximum possible balance factor for any node in T? So remember that a heap is a tree, but it has this fullness property, right? That it is, generally, it looks something like this, right? Here, let me redraw that. It's full. Everything here is full, except for possibly the last level, but that one is full and to the left. So if we have a full binary tree here, full heap, automatically the maximum or the minimum is going to be 0 because everything is perfectly balanced. Now let's suppose that we have something that's slightly unbalanced, right? First of all, could I do something like this? No. That leaves this level right here unfull. So I can't go that deep immediately, but I can do something like this, right? This is still a heap. It is full, except for the last level, which is full to the left. Now, this balance factor has been disrupted right here. That balance factor is going to be 0 minus -1, so it's going to be 1. Okay? Is it possible to have any other balance factors here at all? Right? So is it possible to be skewed to the right? Right? What would that look like? Skewed to the right with no left child, that's not a heap because the fullness property is violated there. So we could have 0, right? We could have 1 in this case. The next one would then make balance it out if we added that one right there, right? So we can have 0 and 1, right? So possibilities are going to be 0 and 1. No others. So the question to what is the minimum is going to be 0. The question to what's the maximum is going to be 1. You cannot have -1 in a heap. Okay. Let T be a 2-3 tree of depth 8. What is the maximum possible number of keys a T can hold? So for this one, all you need to do is go back to the formulas that we covered in class here, where, again, that we derive them by considering that we had 2 keys here. The maximum number of keys would be where we have 3 nodes everywhere. So 2 keys in each node, 3 children, right? And so 2 keys here, there'd be 2 times 3 keys here. I'll say 1 here. In the next level, there would be 2 times 9 keys and so on and so forth until you get down to depth D, at which point it's going to be 2 times 3 to the D, right? And so what is for D being 8, what is the sum of all these things? All you have to do is put it into an expression here. D running from 0, depth 0, up to 8 twice over 3 to the D, right? Divided by 2, which will end up being canceled. There we go. And so this ends, no, wait. I'll leave it at that. And then the closed form of it, they would end up canceling each other out. This will be 3 to the D plus 1 minus 1. All over 2, but then that cancels with the 2 outside there. Right? And so for D being 8, 3 to the 9 minus 1. Right? Pull out your calculators and compute that if you really want to. I would leave it in this symbolic form right here. Okay. Suppose we want to insert keys 1, 2, 3, 4, 5, 6, 7 into an initially empty AVL tree. Give an order that we could insert them so that it would result in no rotations. So if we just insert them in the order that we were been given, 1, 2, 3, 4, 5, 6, 7, right? If we insert 1, 2, 3, well, it'll be 1, 2, and then 3, which is going to be skewed to the right. Remember the balance factors here are going to be 0. This is going to be -1 minus 0, so -1, skewed to the right. This is going to be -1 minus 1, so this is -2. And so we end up doing a left rotation, resulting in 2, 1, 3. Okay? What the question is asking is, how can we put this stuff into an AVL tree so that we don't have that situation, right? And hopefully you can see the connection here to binary search, to arrays and stuff like that, where if you just go to the center here, that's what you want. I want half of these elements to be in the left subtree, half of these elements to be in the right subtree. So optimally, you would choose to insert the median element first because it'll never move, right? So 4, and then go to divide and conquer here. You would take the median of these two lists, and that's what you would insert next. Right? So 4, 2, 6, or 6, 2, doesn't matter. And then you can go in any order here, 1 and 3, and then 5 and 6. And that would not result in any rotations whatsoever, 1, 3, 5, 6. So there's one possibility. There are actually several possibilities here, all of them correct. But the idea is that you would want to insert the medians first up front so that you don't have to do any rotations. Okay? All right. Gomer's at it again. He thinks he's come up with an algorithm to verify that a graph is a binary tree by simply checking that every vertex has degree 3 or less. A degree of vertex is the number of the edges incident on it. Show that Gomer is wrong by providing a counterexample showing that his algorithm is incorrect. So his criteria again is that everything has degree 3 or less. Is that a binary tree? No. Although that has degree 2, 2, degree 3, degree 1, that's but not a tree. Why? Because it's got a cycle right here. There's a counterexample. Okay. Consider the following integer keys. Insert the above keys into an initially empty 2, 3 tree. Be sure to draw the resulting tree configuration after each insert. And then you do the same thing with an AVL tree. So note that down in your copybooks. 5, 6, 3, 2, 7, 9, 4, 8, and 1. All right. I've got it right here. So let's do a 2-3 tree first. 5 and then 6 would result in a 3 node. And on the next one, where we insert 3, we have 3, 5, 6, but it's too full, and so we promote the middle element up, and we're left with a regular old binary search tree here. Right. Then we insert 2. So that gets always inserted as a leaf. All right. So we see that 2 is less than 5, so we arrive at a leaf 3, and we end up inserting it there. The 2 node becomes a 3 node. Now 7, well, again, same situation here, but in the right child. So 2, 3, still a 3 node, and then 6, 7, that becomes a 3 node as well. Next one, 9, well, that comes down here and then goes over there, and we end up with temporarily 5, 6, 7, and 9 in one node. It's too full. So what do? We promote 7 up. That will mean that this becomes that the root becomes a 2 node, and so it must have 3 children. And so by promoting 7 up, we've split this node into two nodes, 6 and 9. And so we have 5 and 7 at the top root node. 2 and 3 are unaffected. And we have 3 children now, 6 and 9. Inserting 4, we come over here, and then we insert 4 as temporarily making it overfull. So 2, 3, 4, 6, 9 are still here. 5 and 7. So in this case, 3 gets promoted up, but we can't fit 3 keys into this one. So the 5 will end up getting promoted up and creating a brand new root. So 5, 3, and 7. And then these all get split out. 2, 4, 6, and 9. Right? That was 4, or that was 4. So 8 would end up getting inserted here, and that becomes a 2 node. And then 1 gets inserted over here, and there are no more promotions after that. All right. What about an AVL tree? So there's the same sequence. An AVL tree, now we're dealing with rotations. So 5 and 6 get inserted. 3 would end up getting inserted over here, and we're still perfectly balanced. Okay? So those are the first 3 steps. Draw them out, each out, whatever. 5, 3, 2, and 6. Now let's go. Now that it's getting a little bit more interesting, let's start noting the balance factors. Balance factor on all leaves is always going to be 0. The balance factor on 3 is going to be 0 minus -1, so 1. It's skewed, but only slightly to the left. 5, balance factor is going to be 1 minus 0. So 1, it's again skewed slightly, but to the left, and we're still balanced here. Okay? 7 is next. So 5, 3, 6, 7 as the new right child of 6. It's still going to be balanced. In fact, it's almost perfectly balanced at 5. The balance factor at 5 now becomes 0. Right? 0. Oops. There we go. Balance factor of 0, 0, 0. This one is still skewed slightly to the left. This one is still is now skewed slightly to the right. Again, -1 minus 0 gives us -1. 9 would end up getting inserted right here. So at that point, now we are unbalanced. This is going to have a balance factor of 0. This is going to have a balance factor of skewed slightly to the right, so it's going to be -1. And then this is still skewed to the right, but now unacceptably so, -2. So what kind of rotation here? A left rotation. And after that, we're done. After we've done that left rotation, we'll have a configuration of 5, 7, 6, 9, 3, and 2. Okay. 4 gets inserted next, and that's the new right child of 3. Now we have a perfectly balanced binary search tree of depth 2. Right? There's no rotations there at all. 8 gets inserted as the new left child of 9. That's not going to cause any disruption, because if you did do a rotation, right, where's it going to go? Something necessarily needs to come down over here. So everything is balanced there. And then 1, then 1 becomes a new left child of 2. Again, no rotations there. Okay. All right. No questions so far. So we don't have time to go over the other midterm, but I can show it to you and show you what it looks like. It's very, very similar. This is from 2019. So here's some gimme points. How many subsets of size 10 are there with a set of size 82? How many permutations are there of 24 objects? So there are only 5 points. Some basic graph operations can have different efficiencies depending on whether or not they're represented as adjacency matrices or adjacency lists. Oh, sorry. Thank you. There we go. Determine whether, create an algorithm to determine whether or not a graph is a complete graph, and design pseudocode under the assumption that it's an adjacency list versus an adjacency matrix. Okay. I probably would not ask a question like this, knowing that many of you probably did not cover this in 235 in spring, but if you have seen it before, then you should be able to do something like that. Suppose an algorithm takes a graph, 2 vertices, x and y and k, and outputs true if x and y, and if there's a path connecting x and y of length k. So how could you use that algorithm, kind of like what we did with independent sets? How could you use that algorithm to solve the Hamiltonian path problem? Hopefully you understand that you would go over all pairs of vertices and ask for k being n minus 1, because that's what a Hamiltonian path, the length of a Hamiltonian path is. More keys inserted into a min heap and show us what it looks like. Insert it into a 2-3 tree and show us what it looks like. Insert it into an AVL tree and show us what it looks like. Insert it into a hash table and tell us what it looks like. That's all it was back then. I believe in 19 it was closed computer, so that's why we asked those kind of questions. Of course, you're free to use a tool. That's why, but understand, I'm not going to ask those style of questions. I'm going to ask something where you have to think about it a little bit, or you have to know what you're doing. You can't just plug it into one of the simulations or the visualizations and expect it to spit out the answer. All right. Okay. Again, no live stream tomorrow, but I will have extended office hours during the same time, 11 o'clock to 12:30 via Zoom. Good luck, and it will open tonight at midnight.